Hey, it's Dr. J. We just get right into it without any hesitation. The main tool in this section is to rewrite into exponential form. So that technique of going from a logarithm into an exponential form is going to be our main tool. It's going to be the key to solving all of these logarithmic equations. So keep in mind that if you have a logarithmic equation, you're going to rewrite it into an exponential equation by saying that x is equal to a to the y. And that is how you're going to get your hands on the value of x. Remember, these mean the same thing. Tomato, tomato. Yeah. Although it's more like looking at the underside of a tomato. Yeah. It's like this is the top and this is the bottom of the same tomato. Yeah, it's two sides of the same tomato. All right. So let's just get right into it. Example 1. Solve log base 2 of x. Log base 2 of x is -1. And what does that mean x is? Well, just use this idea. Your base is 2. Your argument is x. And so x would be 2 to the -1, which you would write as 1/2. Let's do a few easy ones to kind of get the idea going. How about log of x is 3? If you don't see a base, base 10 is implied. That's what we call the common base. So you're going to say x is equal to 10 to the 3rd power, or x is equal to 1,000. So notice, to solve a logarithm, you use an exponential. Just like in part 1 of this video, to solve an exponential, you use a logarithm. So in this one, this is what we call the natural base. So that would be base e. The natural base. You would rewrite this as x is e squared. Now this actually has two different versions of the answer. Because e is a decimal, this is what we would call the exact value. Or if instructed, round to 4 decimal places. So x would approximately be 7.3891. Again, only do that if instructed. If the question says exact, well then you can just leave your answer as e squared. But if instructed, most of the time, if I ask for a decimal, I'll typically ask for 4 decimal places, so 7.3891. All right, those were the warm-up problems. That's just to get you used to going from a logarithm, identify what base you're using, and then turn it into an exponential in order to solve it. They're going to get a little bit worse as we go along, or a little bit better, depending on how you're looking at life. All right, let's try another one. 3/4 log base 5 of x is equal to -2. Now, in order to use the rewriting principle or the conversion principle, taking it from a log and writing it as an exponential, you first have to get rid of any external operations such as multiplication, division, addition, subtraction, things like that. So you have to simplify it first. So we're going to multiply both sides by 4. And then we're going to divide both sides by 3. Sometimes you can speed up the process a little bit by doing those at the same time. And now you're going to rewrite this using your exponential. So the base is 5, and the power is -8/3. Now, I want you to actually calculate what that is. So that's 1/5 to the 8/3, which is 1 over the cube root of 5 to the 8th power. Remember, the denominator is the root. It's been a while since you did this. The denominator is the root. It's a cube root. And the numerator of the exponent is the power. So we did a cube root and an 8th power. So I've got 5. Do the cube root first. So that'll be 1.7099 blah, 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 blah to the 8th power. I'm just going to keep this all in my calculator here. 1.7099, and then I'm going to raise it to the 8th power. So 73.10044. And then I'm going to do 1 divided by that. So 0.01367. And then I run around this to 4 decimal places. So my dictator is the 7. 7 is definitely bigger than 5, so I'm going to round up. The 6 is going to round up to a 7. Okay, so my exact solution is 5 to the -8/3. My approximate solution is 0.0137. How about this one? 2 log base 4 of x is equal to 3. Before you apply any exponentials, make sure you get rid of any multiplications or divisions or additions or subtractions. So we're going to divide both sides by 2. All right, now we can use our exponential notation. The base is 4, and the power is 3/2. So that, we don't have to worry about the reciprocal because that power is positive. So that'll be the square root of 4 cubed. This one you don't need a calculator for because the square root of 4 is 2 and 2 cubed is 8. So no approximation is necessary. You just get an exact value of 8. So you're only going to need to use your calculator, well, in two cases. One, if I tell you to. It clearly says round to 4, that's a clue. But the other one is if you must use your calculator. If there's no other way to calculate it, well, that's why our ancestors invented these calculators, to give us another way. Although, your great-great-great-great-great-grandmother or grandfather didn't have a calculator, and they were still able to do this stuff without calculators. So it's really become sort of a comfort food than a necessity. How about this? ln of 3x minus 4 is equal to 0. Again, you need to get rid of any multiplications, divisions, anything that's happening outside of the logarithm. You want to get rid of that. So we're going to add 4 to both sides. And then we're going to take the exponential, base e. So 3x is going to be e to the 4th power. The base is e. And then we're going to divide by 3. So this is your exact solution. You can't do that without a calculator, although you can, but it's just a little bit out of our scope. So e to the 4th power is approximately 54.59815 divided by 3. So x is approximately 18.1994. That would be our approximated answer. I hope everybody is catching on to the main concept, which is that when you have a logarithm, you clearly identify the base, and then you just rewrite your equation, and x just sort of falls in your lap. I like to think you don't have to go looking for x. X comes and finds you. Right? You just have to be there for x to come to you. Four log of x minus 5 equals 8. Okay, so anything that's inside the parentheses, that's going to get affected last. So we're going to move that over at the very end. Anything that's outside the parentheses, you want to move right at the beginning before you do the exponential part. Look for the base. The base is your clue. So this one is base 10. So base 10 to the 2nd power. And then the logarithm is gone. You have rewritten the logarithm in terms of base 10. This one does not require a calculator because you can all do 10 squared in your head, which is 100, and then add 5, and you get 105. So no approximation is necessary. This is an exact answer of 105. Okay, the last few examples all require a relatively good understanding of the properties of the logarithms. Okay, so we're going to apply the property of the sum. Sometimes referred to as the sum to product property. And so we're going to take the two arguments and multiply them together. So now your argument is x squared plus 3x. Well, in this problem, both sides are base 6. So we can rewrite both sides using the base of 6. You have to use the base on both sides of the equation that we were given. 6 and a log 6, those are inverses of each other. And so now when you rewrite it, your exponential function just literally disappears, and you get x squared plus 3x and equals to 5. Now you can solve this equation by any means necessary. I'm going to use the quadratic formula. You can also try factoring. You can try completing the square. You can try whatever you like. So use the quadratic formula if necessary. Sometimes you get lucky and this is factorable. So try to factor it first. Okay, so we got x squared minus 3x minus 5 is equal to 0. You can use the quadratic formula on any quadratic equation, but I recommend only using it if it's necessary. You should always try factoring. I mean, you might find that, it's factorable, and it will save you a lot of time. So just take a quick guess. Don't spend too much time on it. I'd say maybe a minute, 2 minutes. I'm only going to spend a second or two on it. So obviously, x times x is x squared. Try and find two numbers that multiply to be 5. All right, 5 times 1. And then multiply to be 5 or negative 5, and then add to be positive 3. It's impossible. So again, if it's not factorable, don't sit there and drive yourself nuts over it. Just move on and use the quadratic formula. So we have x is equal to negative b, so negative 3 plus or minus the square root of 3 squared minus 4 times a is 1, times c, which is negative 5. Be really careful with your signs. So you know who a, b, and c are. A, b, c. I know I don't need to teach you the quadratic formula again. You already learned it. Maybe you're a little rusty. I don't know. And then don't forget all over 2a, so 2 times 1. So these are your solutions, or at least your potential solutions. We call those the candidates. Let's clean them up a little bit and see what we're looking at. So 3 squared is 9. Negative 4 times 1 times negative 5 is positive 20 over 2. So we have negative 3 plus or minus the square root of 29 all over 2. So these are our candidates. You can use a calculator to determine which ones, or what they look like as decimals. So let's see, we're going to approximate, do the square root of 29 first. That's about 5.3852, I guess. So x is approximately negative 3 plus or minus 5.3852 over 2. So that would be candidate number 1 would be, let's see. So let's do the negative one first. So that'll be negative 8.35, excuse me, 8.3852, and then divided by 2. So that'll be negative 4.1926, I guess. And then our other candidate is, oh man, I got to start over again. So I got 5.3852, and then we'll do the positive one. So that'll be 2.3852, and then divided by 2 would be 1.1926. Now, in previous chapters and lectures and sections and such, I'd said, you know, if you do everything correctly, you know, back in chapter 2 or maybe even chapter 3, you do everything correctly, you get the answers, you can just walk away, right? These are the answers, right? But not in chapter 6. Chapter 6 is the check every answer chapter, all right? Especially on the test. You got to check because they could both be right, or maybe just one of them is right, or perhaps neither one of them is right. Yeah? So we got to check. So what was our original equation? Original was, what was it? Log base 6 of x plus log base 6 of x plus 3 equals log base 6 of 5, right? That was our original. You must go back to the original form of the equation. You can't take any of your simplified versions and use those. So these are our candidates, right? We don't know if they're right or not, so let's check them. All right. Now remember, the domain of a logarithm is all non-negative numbers. Yeah. Actually, to be perfectly honest, positive only. 0 is not even counting, but in general, it's non-negative. So I can already tell when I go to plug this candidate in, I get log base 6 of negative 4.1926. It's already false. It doesn't matter what happens to this. It's already false. All right. If one term is false, the whole entire equation is false. You can't be like, oh yeah, this term's false, but this term's still true. That doesn't work like that. All right. One false statement makes the entire argument false. Okay. So that's it. So this candidate has failed. It's no good. All right. Let's check the other one. The other one looks positive, so it's got potential, but that's not a guarantee. It's just, it has more potential because it's positive, but it still has to be true. All right. So remember, we're just checking, question mark, does this equal log base 6 of 5? All right, my 6 is kind of small down there. There we go. I don't know. I'm checking. I don't know if it's true or not. Don't assume that it's true. That might not be true. All right. So now let's see, does this make sense? Okay, so let's combine these together. This would be log 6 of 1.1926 plus log 6 of 4.1926 equals log base 6 of 5. And so this would equal log base 6 of 1.1926 times 4.1926. Now you got to be careful here. These are decimal points, and this is multiplication. So sometimes when that happens, I like to just switch to parentheses so it's clear. All right, 1.1926 times 4.1926. And what do you know? You get 5. All right. Now, it'll be approximately, I think the reason is obvious. I hope we already did an approximation 5 minutes ago. And so obviously, it's not going to be exactly 5. It's actually 5.000009. That's still 5. All right? That makes up for the fact that we estimated in the first place. We approximated in the first place. Good. All right, good. So the candidate, so the solution now is 1.1926. And that's our solution. Moving on, next example. Actually, this is number 9, isn't it? Example 9. So again, we're going to use that property. The sum becomes a product. All right. You don't have to worry about this side. This side's done. Now you're going to distribute. I don't see a base, so I assume the base is 10. So base 10 on both sides. Going to cancel out. And you just get 7x on the right side and x squared minus 4x on the left side. You can do this anytime that they have the same base. Yeah? Two logarithms with the same base, you can raise them to that same power, whatever the base is, and then you no longer have the logarithm or the base. Yeah, they've undone each other. I'm going to solve this one by setting it equal to 0, and then you can decide how you want to do it from there. You can either use the quadratic formula, or you could try factoring. I always think you should try factoring first. And the last time it wasn't possible, so I had to use the quadratic formula. But this time it's possible. I could just factor out an x, and I get 2 solutions, or 2 candidates. I get x equals 0, or x equals 11. Now plug them in here and make sure that they remain positive after you've plugged them in. Okay. So let's try 0. All right. Plug 0 in here and here. If you plug in 0, does that remain positive? No. Yeah. 0 minus 4 is not positive. In fact, you're supposed to put a 0 here as well. Yeah. None of these are positive. So 0 is no good. You cannot have 0. Yeah. Okay. Try 11. All you got to do is make sure that it remains positive. You don't actually have to do all the math. Just eyeball it, inspect it, and make sure that it equals a positive argument. So is that positive? Yes. Check. Positive. 11 minus 4? Check. Positive. Yep. Check. Positive. They're all positive. If all arguments are positive, then your answer is valid. So my solution is x equals 11. If any of the arguments come out to be negative, all it takes is one negative argument, the solution is invalid. You cannot have a negative argument. We've come to the end, my friends, the bitter end. Example 10. This one is log x plus 5 minus log x plus 3 equals 1. My eraser probably can't handle another lecture. It's done. All right, so this is the quotient property. The difference of the logs is the log of the quotient. Quotient property. Now make sure you write the logarithm one time. Also notice that there's no logarithm on the right-hand side. Yeah. So there's no log on the right-hand side. That means that this process is going to be slightly different than the last one. That means that the base is only occurring on one side. So when I apply my base of 10, invisible base 10, remember? It's invisible base 10. It's going to cancel on the left-hand side, but it's not going to cancel on the right-hand side. Because if there's no log, then there's no cancellation. And so now you have x plus 5 over x plus 3 equals 10 to the first power. 10 to the first power you can simply write as 10. If this was 10 to the second power, then you would write it as 100, and so on and so forth, depending on what it is. Solve this equation, and then before you submit it, go back to the original and make sure that the arguments are all positive. So we're going to solve this by multiplying both sides by x plus 3. And I think you can take it home from here. You're going to subtract x from both sides. Or you could subtract 10x. I don't really care how you do it. You get 5 equals 9x plus 30. That's if you choose to subtract x. If you choose to subtract 10x, then you're going to end up with a negative 9x on the other side. And I think that on the last day of school, you probably know that by now, I hope. You're going to subtract 30 from both sides. Okay. So that gives you negative 25, and then you're going to divide by 9. So x is negative 25/9, which is negative 2.7 if you like. So we're going to check. When I'm checking, I only need one decimal point to check. This is the actual answer, negative 25/9. But when you go to check, it's much easier if you use a decimal. Now be careful. I have had students panic because they're used to kicking out the negative answer, right? They remember that the answer is not supposed to be negative. But it's okay for the solution to be negative. All you're checking is that the arguments don't turn negative. Don't let the argument turn negative. Keep the argument positive. That's a good rule. So negative 2.7, plug it in right here. All you have to do is make sure that the arguments don't turn negative. All right. Negative 2.7 plus 5. Is that positive? Yep. Yes, it is. Negative 2.7 plus 3. Is that positive? Yes, it is. So even though my solution is negative, when you plug it in, if the arguments remain positive, all arguments are positive, so the solution is valid. So x equals negative 25/9 is valid. Okay, folks, that is the end. That is the end of the semester. That is the end of 6.6. I wish you all the very best. Your final exam is next Thursday, May 21st, and it covers everything. Okay, so study all your old tests, study your homework, watch the videos, and on Thursday, log in. It'll be due by 11:59 p.m. It has been my great pleasure to have been your instructor. I'm sorry things turned out the way they did and we had to be apart for the last month or so, but I hope you were all able to stay on top of it. Do your homework, do your best, and we'll let we'll let fate decide. We'll let the universe decide what's in store for you. So I wish you all the best. Cheers. Dr. Jordan signing out. Maybe I'll see you around when this is all over. Bye-bye.